So here we're looking at some finite geometric sums. So this is our infinity symbol, so we're considering an infinite number of terms is equal to the first term divided by 1 minus the common ratio. Note the common ratio must be between 1 and -1, and the absolute value of r must be less than 1, and the common ratio can't be equal to 0. This idea will come up in your homework, so just keep that in mind. So we want to find the sum of this infinite geometric series. How do we know it's infinite? Because it goes dot, dot, dot. We know it's geometric because I'm multiplying by 2/3, it looks like, because 2/3 times 4/3 is 8/9. If you don't know that, you could obviously do the common ratio, which is 4/3 divided by 2, which is the same as 4/3 times a half, which is equal to 2/3. So our infinite sum will be equal to the first term, 1 minus 2/3, which is equal to 2, and this is 1/3. And if I flip and multiply, I get 6. The next one, notice that it alternates between positive and negative. Our first term is 2. Looks like our common ratio is 1/4, because a half divided by 2 is equal to a half times flip and multiply this, so that's a half, which is 1/4. So there's our common ratio. My first term is, this is negative. So that should be -1/4. That's a sad looking negative. So my infinite sum will be equal to the first term, 1 minus a -1/4, which is equal to 2 over, and this is 1 plus 1/4. So this is 2 over 5/4, and if I flip and multiply, I get 8/5. Number 3, first off, we know it's we're finding a sum because sigma denotes sum. We know it's infinite because obviously the number of terms is infinite. The question is it geometric, and if so, what is the first term in the common ratio? So let's calculate a couple of the values here. When k is equal to 1, we get 1/8 times 2 to the first, which is equal to 1/4. Our second term will be 1/8, and this will be 2 minus 1, which is, oh, did that wrong. Clear that up. Start again. If I plug in 1 here, I get 2 to the 0. So 1/8 is 2 to the 0. So that's equal to 1/8. This is 1/8. Plug in 1 here, you get, plug in 2, you get 2 to the first. That's 1/4. And the next one will be 1/8 2 squared, which is equal to 1/2. Why did I write down 4? Half, and 1/8 2 cubed is equal to 1. So notice that my numbers are getting bigger here, and it looks like my common ratio is actually 2, but let's verify that. Common ratio is 1/4 divided by 1/8. So if we flip and multiply, we get 1/4 times 8 over 1, which is equal to 2. Since my common ratio is bigger than 1, we can't find the infinite sum. And if you think about it, if we were to have an infinite number of sums where we're doubling each one of our values as we go along, not only would the last value in our sequence or in our sum be really huge, because this would be 2 to the infinite power. If I tried to add up all the values before that, it's going to get even larger. So therefore, since the common ratio is bigger than 1, you can't find a sum of a geometric sequence, because each term just gets bigger and bigger and bigger, and the sum just gets too large. It gets without bound. So therefore, since the common ratio is bigger than 1, we can't find the infinite sum. Next, here is a repeating decimal that goes on forever and ever. I'm going to rewrite it as 0.257257 dot 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 dot. And I'm going to rewrite this sum as this decimal representation as 257 plus. I'm going to cut this off and just add the next 3 repeating, which would be 000 257 plus. Now cut those off and have the 6 zeros for the previous term. That's a 5. So notice that if I add this to this, I get this 6 digits, and if I add this one plus this one plus this one, I get these 9 digits, and if I was to continue on, I'd get all the digits. So I'm just writing this infinite repeating decimal as just a sum, but it's an infinite sum because it has dot dot dot, and obviously this goes on forever and ever. So let's see, is this actually geometric? And it is. The first term is obviously 0.2557. Excuse me, 25.7. The common ratio is just the quotient of two consecutive terms, so let's just divide. And I just did this using my calculator. I get 0.001. So, therefore, my infinite sum is equal to the first term, which is 25.7 over 1 minus 0.001. which is 25.7 over 0.999. And hopefully you'll see that these decimals cancel out, because this is really 257 over 10 hundredths thousands over 1,000. 999 over 1,000. And notice that these two cancel, so you're just left with 257 over 999. So the next thing I would do is just put this in my calculator, hit the old frac button, and see if it simplifies, and it doesn't. So this is a rational representation of a repeating decimal. So therefore this is equivalent to this, hence that's why this is considered a rational number, and so is this. Rationals are just fractions. So rationals can come in the form as a fraction, or they can come in the form as a repeating decimal. But these two are equivalent, and how did we able to determine that? By using the idea of an infinite geometric series. So likewise, this next problem here, we have this non-repeating part, and then we have this repeating decimal over here. So using this same idea here, in terms of holding decimal places for the previous term, I'm going to write this as 1.2. So I'm going to cut off the non-repeating part. Then I'm going to write this as 0.038. And then the next decimal term would be 3 zeros, representing the 3 digits previous to it. And then the next repeating part, which is 38, plus these decimal places, so that's 5, 38, and then it continues. So my infinite geometric sum starts here. This term here just kind of goes along for the ride. Here's my repeating decimal piece, so I can figure out the common ratio by taking the quotient of these two terms, 0.0038 and 038, and when I divide those two, courtesy of my calculator, I get, I believe, 0.01. Correct, 0.01. So therefore, my infinite sum is going to be equal to 0.038, 1 minus 0.01. I hit my frac button in my calculator, which I didn't do, which is equal to 19 over 495. Add that to this non-repeating part, 1.2. Courtesy of my calculator, is 613 over 495. Okay, for our last problem here, we have a ball that is dropped from a height of 30 feet. Each time it strikes the ground, it bounces up 0.8 of the previous height. When the ball stops bouncing, how far has it traveled? So we're looking, when we say how far has it traveled, how far has the ball actually traveled? Well, if you think about it, this is our visual, where this distance is 30. So the ball drops 30 and then bounces up 0.8. So 30 times 0.8 would be 24. Obviously not to scale. And then it bounces back up and then bounces back up. And we're assuming that it continues bouncing an infinite amount of time. So my first term is 30 and the common ratio is 0.8. So my infinite sum will be 30 over 1 minus 0.8. So 30 divided by 0.2 is going to be 150. So 150 is actually not our final answer. 150 only represents half of this distance. So it represents this one, and then it bounces back up, and then it represents plus this, plus this, plus up, plus up, plus up. So we didn't consider the downward piece of this ball. So the ball actually travels twice 150. Oops, that's times 2, which is, so therefore it's now traveled 300 feet. Well, by multiplying by 2, we represent the bouncing up and bouncing down, bouncing up and bouncing, that going on an infinite amount of times. However, when we multiplied this by 2, we only wanted half of this. We didn't want this piece going up and down because it's dropped from initial height of 30. So therefore, we didn't want to double this piece here. So we want to subtract off 30. So therefore, our final answer is 270 feet.